So in the last video I said there's a faster way to do this previous problem. Let's see it. It's called the tabular method. And sometimes, in some cases, you can use this for what we call embedded integration by parts, or sometimes people simply refer to this method as by parts. How does this work? Okay, well, it involves a table. All right. So if we look at that last example, integral x to the third over e to the x dx, which we immediately rewrite as x to the third e to the negative x dx. Okay. Now I've got the final answer out on the side here. Don't worry about that. You'll see that where this comes from in a second. Here's how the table works. You have three columns: the sine, u, and dv. So to fill in the first row, and you can kind of see my erased work here, but ignore that. All right, to fill in the first row, it starts the sign, we're thinking positive, negative. It begins positive. And then we've got our choice for u, and our choice here, if you remember, was x to the third. And our choice for dv, e to the negative x. Okay, and then here's what we're going to do. We're going to create more rows by taking derivatives of u and by taking antiderivatives of dv. And every time we do it, the sign alternates. Okay, so the next one's going to be negative. And then derivatives for the u, so 3x squared. Antiderivatives here, negative e to the negative x. Okay. Then we're going to go again. It's going to be positive this time, alternating. Then derivative, 6x. Antiderivative, well, that negative just disappears again, right? And we're going to keep doing this until our derivatives hit 0. When the derivative hits 0, then stop. And let me show you thinking. So we've got our sign changing, positive, negative. It always begins positive. The u column, take derivatives. The dv column, take antiderivatives. And then we can get our answer straight off of the table. And you can see it. It almost fits on the screen. Well, you see the final answer there. Okay, how do we get to the final answer? Here's how you read it. You start with the sign, go over, and then down. So these three multiply. That's the first term. It's positive x to the third times e to the negative e to the negative x. Then the next part, we take these. Minus 3x squared e to the negative x. Minus 3x squared e to the negative x. And we keep going until we get to this. So we avoid the 0. We get to that. Okay. So then what comes next? Plus 6x times negative e to the negative x. And finally, minus 6e to the negative x. And be sure to throw a plus c on the end there. Don't forget that. And if you simplify, you'll have it. What do we got? Negative x to the third e to the negative x minus 3x squared e to the negative x. 3x squared. Minus 6x e to the negative x. Minus 6e to the negative x plus c. And wouldn't you know it, that's the same answer we got up above here. They were all subtracted, right? Minus, 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 minus. Yep. For this one. Pretty nifty. Now, for some reason, our textbook does not present the tabular method. I don't know why. This is a well-known method. I don't know why our textbook and our author doesn't mention it. Go figure, but you guys heard about it anyway. Okay, now if you're thinking, hey, does the tabular method, does that always work? You know, if there's more than one integration by parts, can we just always do tabular? And the answer is no. This only works on certain styles of integrals. And let me show you those here. Tabular works for if you have a power of x times e to the ax. Sorry, that's a little bit blurry. E to the ax. So you might have some number times x. We had negative x, right? X to the third, e to the negative x. Or it might be x to the n times the sine of ax dx. Or it might be the integral of x to the n cosine ax dx. Now, in every time, you know, you see the pattern, right? That power of x in the front. You're always going to pick u to be the x to the n, and then you take derivatives, and eventually you'll get to 0. The dv is going to be the other part, either the e to the ax or the sine or the cosine. And then that tabular, that second column, those derivatives going to hit 0, and you know when to stop. There are many cases where you might use integration by parts 2 or 3 times, yet it's not one of these styles here. Yeah, I do it the long way. Okay, hey, let's try one. Now you see here, let's try something different. Now you see here, like, you know, we haven't done anything with sine and cosine. You get more of those in the homework. Let's combine e with sine. This will be good. This is going to be this will be interesting. Part D in our examples. The integral of e to the x sine 2x dx. All right. Well, I don't know. You know, we just have to take a guess at u, what's going to be u, and what's going to be dv. And at first, we're really probably just stabbing in the dark. And it's only going to be a few steps in that we can tell. It's a lot like u substitution, right? When you first learn u substitution, you're like, what do we pick for the u? And, you know, there's some insight you get as you do more of those problems. But at first, you know, you're just kind of, I don't know, I'll try this for my u substitution. And maybe it works, maybe it doesn't. Same thing with integration by parts. You know, you just pick your u and your dv, and maybe you can get it to work and maybe not. That's just part of life. It's just how it goes. Okay, let's see. I think I'm gonna just go as straightforward as I can as a first guess. I'm gonna pick u to be. Oh, I picked it this way. Okay. I thought I'd picked it the other way. All right. Let's try it like this. Let's take u as sine 2x and dv as e to the x dx. Actually, okay, I remember why I pick it this way. So if you think about it, I would rather take a derivative of sine 2x than an antiderivative. And there's some insight, you know. I don't mind taking derivatives or antiderivatives of e to the x. Sine 2x, though, I'd rather take a derivative with the chain rule than have to do the chain rule in reverse and involve fractions. So this is going to play out just a little bit smoother if we take the sine 2x as the u, since derivatives will then be, you know, have a 2 in front. Okay, let's see. What are... Oh, looks like a little typo here. This is du. My mistake. What are du and v? Okay, so let's see here. Sine 2x. Well, then du would be 2 cos 2x dx. Right? With the chain rule happening. Dx on the end. Here, antiderivative, well, that's That's manageable. That's just e to the x. Okay. So our first step, uv minus integral v du. So we've got sine 2x times e to the x minus integral, put a dot there, times, minus integral e to the x times our du, 2 cosine 2x dx. And let's clean this up a little bit and see if we're going in the right direction. Okay. So you see I've circled the new integral, but let's check this out. I'm going to put the e to the x in front. All right, e to the x sine 2x minus, bring that 2 out, e to the x cos 2x dx. Okay. Well, let's see. Let's compare this integral with the original. Did it get easier? You say, well, all that really happened was sine became cosine. That's it. Okay, so I don't know if we can argue it got easier, but did it get harder? Well, no. Sine becomes cosine's not harder. Okay, if it didn't get harder, we're actually going in the right direction. Usually it will get easier, but there's something about this problem that is kind of strange. And it's a good thing for us to highlight. It didn't get harder, but it didn't get easier. Okay, well, let's keep going and just see how this plays out. So you see I've circled the new integral. What's going to happen? So we're going to have to do integration by parts again. And we're going to be consistent with the way that we did it the first time. Okay. So we're going to pick, if we picked u to be sine 2x, here we need to pick u to be the cos 2x. And the dv is going to be identical. Okay. So let's see here. U is cosine 2x. So what is du? Well, take a derivative, right? And cosine goes to negative sine. So this becomes negative 2 sine 2x. And here, well, it's the same antiderivative. Just v equals e to the x again. Okay. So let's see how this plays out. All right, so we've got u times v, and I just wrote that, let's just put the e to the x in first. E to the x cosine 2x, okay, minus v du. And, well, we're subtracting a negative, so let's make that plus, and then that 2 will come out in front. Hopefully you follow that integral. There's our v, and then the other half of du, e to the x sine 2x dx. So there it is a second time. Hey, do you notice something here? That's the same place we started at. That's the same integral. E to the x sine 2x. Okay, something's up here. This is really bizarre. We came around, and now we're looking at the exact same integral that we were asked originally. We cycled back to it. Does that mean we're doing something wrong? No, it actually means we are almost to the answer. What? Yes. Okay, we're not going to do another integration by parts, right? Obviously, that would just lead us back here and we go around in circles. There's a new approach. That's the original. Oh my goodness. Okay, let's go back. Let's put this whole thing in right there, and we got these 2's we got to multiply out. Let's do this, okay? So here's the original, okay, on the left side. That integral is equal to, and now we start here. We've got this part minus 2 times, And that 2 times applies to this whole thing with big parentheses around all of it. Parentheses, parentheses. Okay, so all of that going in here minus 2 times all of this. Okay, let's pull this up now. Here's what we're going to do. We're going to distribute this negative 2. Okay, so here's the left side. Integral e to the x sine 2x dx. That's our left side. We've got that part minus 2 times e to the x cosine 2x. Sorry, some of my writing is very light. And then we've got minus 4 times that original integral. Okay, check this out. Let's add this whole thing over here. Add this to both sides. And it will combine. And I think I've got this on the next page. Let me keep this. Ooh, this is so exciting. Okay, so when we add that 4 times that integral, we've got 5 of the original integral equals, and then we've got these 2 parts. So I'll give you a moment to write all that. And now, this is easy to miss. When you add that over to this side, you're leaving behind the plus c that would have gone on the end. And it's usually not written before you do the antiderivative of that final integral, but there is a plus c out here implied, and so it's going to leave that. We need that here on the end, right? This is the answer to an integral, so we need that plus c. Now we're just one step away. If 5 times this integral equals this, can't we just divide both sides by 5? And we got it. So integral e to the x sine 2x dx equals 1/5 e to the x sine 2x minus 2/5 e to the x cos 2x plus c. And we did it. A very sneaky, slippery problem. Very deceptive. You end up repeating the same integral once you get to integration by parts in, but that's how you get out of it. Simplify, add it back to the other side, and then divide by that constant. And we did it. Okay, we've got one more example of a definite integral next.